AI models in the next few years, is scale all you need for continued progress? Let's investigate. If you've been keeping up with AI, you might have noticed that AI bros and gym bros had one goal in common: getting huge. So I wanted to find out in a focused manner, what exactly is the current consensus and where are companies betting their revenues on? The reason this is important is our lives are becoming increasingly dependent on AI, whether you're in the field of AI or not, and I think it would benefit everyone to have at least a rough idea of what form, shape, speed AI progress is going to come in the next few years. So as one does, I did a deep dive into this topic, reading countless articles, papers, and interviews. But the biggest task of all of this was actually trimming away all the tangential stuff. These are some of the interesting topics that I had to intentionally omit, but eventually we'll have to come back to another day. Eventually, I found 3 important papers that helped me understand where scaling is going. But in order to discuss those, I first have to explain a few basic concepts. So I'd like to start off by dividing the field of AI into 5 distinct eras. Note that there are many overlapping and other important approaches being developed during these stages. But for the sake of simplicity, let's divide it up like this. Before 2012 was the age of machine learning. From 2012 to 2017 was the age of deep learning. And 2017 to 2021 was the age of the transformer. 2021 to 2024 was the age of scaling. And from here on out till probably around 2030, will it be the age of synthetic data, massive compute, agent environments, new architectures, or just continuation of model scaling? Really, this is what I want to find out. In 2019, Richard Sutton criticized the field of AI research for failing to learn the bitter lesson. And that bitter lesson was that using lots of computational power often works better than trying to program human knowledge into AI. Sutton explained that smart researchers often try to make AI think like humans. But over and over again, really what works the best is using more powerful computers that try to learn. For example, early chess programs tried to copy how human chess masters think, but in the end, what worked best was having computers do a deep search of all the possible moves. With language understanding, initial efforts were focused heavily on parsing grammar and trying to use traditional linguistics to program a system that could understand language. But surprise, surprise, ultimately what worked was more computation and massive data sets that learn language. In defense of the expert systems researchers, it is often the case that computing has always been very expensive. And, at the time it feels like you can make faster progress with programming. But in the long run, due to Moore's law, computers get more and more powerful, available, and cheap. So if expert systems fail time and again, what are some methods that actually deliver? This happens in different domains like computer vision, language, chess, Go, video games. The thing that works pretty much every single time is search and learning, which are both very compute intensive. So the main takeaway from Richard Sutton is, instead of trying to manually enter the information, build systems that can learn the information. And we can still use expert systems to evaluate AI systems. So I believe this is a generally agreed upon principle by which most researchers conduct their work nowadays. Thanks to Moore's law, we have more compute, so we can start to increase our model size and dataset size. And it's generally agreed that model size and dataset size lead to better performance. Here's an analogy. In biology, the more neurons we have in language areas of the brain, the more capable the animal becomes at processing language. It's also cool to see that GPT-4 is on a similar scale to human language areas. The implication from all of this is that the bigger the model scale, the more performance you can get from it. The way I like to understand it now is that the model size is the capacity to learn, dataset size is the information to learn. So the first paper came out in 2020, and it's called the Kaplan scaling laws. The main key finding from this paper was that performance improves as compute and dataset size increase. But this one emphasized the compute more, and generally suggested that larger models are more sample efficient, and this paper really influenced the development of GPT-3 and other large language models. Then came chinchilla scaling laws from 2022. This one focused more on finding the optimal ratio between model size and dataset size. And the findings were that optimal model size scales linearly with dataset size, and that most large language models are undertrained. This means that the number of tokens or dataset size it was trained on was much smaller than the model's capacity to learn. So to put this in practice, they're giving a ratio of 20 tokens per parameter. So something like GPT-3, which had 175 billion parameters, could have been trained on 3.5 trillion tokens. However, in reality, it was trained on 300 billion tokens. And GPT-3 gives us a ratio of 1.76 tokens per parameter. Now, GPT-4 is rumored to have had almost 1.8 trillion parameters and 13 trillion tokens, which gives us a 7.22 tokens per parameter, which shows improved generalization. Another way to put this is to say that as of right now, quality and quantity of data is the biggest bottleneck. So key takeaways from both papers. Kaplan scaling laws basically said that a bigger model means more performance is the important factor. And chinchilla's scaling laws provided how to scale dataset size with model size. And they both provide a guide for us on how to understand how AI companies are scaling their AI systems. Combining these, we can also come to the conclusion that we can build a much more efficient and smaller model that'll be just as capable, if not more, than a large model that uses a smaller data set. Chinchilla is basically saying data matters more. Then there's the issue of compute. Since AI research right now is a very empirical science, where researchers come up with a hypothesis and they want to test it, and the way to test it is to run a significantly big neural network. And since compute is very expensive, companies will often want to use their limited compute time either for doing experiments or training a model that'll eventually generate money someday. So they have to kind of balance that and think about both, because they also don't want to be left behind, because there's a huge incentive to beat the competition to new findings. So that's the main compute bottleneck. In summary, expensive compute is bottlenecking research, and quality and quantity of data is bottlenecking model performance. Now, remember how I said GPT-4 was using 13 trillion tokens, and from GPT-3, which was using 300 billion, while that may seem like a big jump in data, in reality, OpenAI was using some of the data repeatedly on each of the different expert models for GPT-4. I even heard that sampling high-quality reasoning text multiple times led to increased reasoning capabilities. And as of a few days ago, OpenAI made a deal with Time magazine to use all of their data. So we may increasingly see people with proprietary data sell their data to AI companies. And that would be the single most important ingredient to AI companies right now. So I think by now we can all agree that scaling model size with high quality data on a ratio of 1 to 20 will probably keep improving AI. But if we keep doing this, the performance graph as we scale both data and model size will be exponential, linear, or logarithmic. And where are we on that graph? Well, there was another paper that wanted to find this out. And the ultimate test of intelligence and usefulness from these models would be the zero-shot learning capability. Basically, can the AI be used in a completely new scenario and reason well enough to give the correct answer? And the key finding was the logarithmic case. So what does that mean? Well, first, where we are on the graph matters. Because if we're really early in the graph, that means we have probably several generations before we start to see a plateau. And since the graph is logarithmic, we'll probably see diminishing returns in several generations. So that's interesting. So exactly where we are on this graph, I have yet to find any information on. If you do, please leave a comment below with the source. However, there are still other lessons we could take from this. This finding suggests the need for different approaches beyond just scaling data and model size. I'm seeing a lot of people move to the agent space, so that may be the next era of AI. If you'd like to learn more about that, please leave a like and subscribe. And if you want me to research any topic you think is interesting, leave a comment and I'll do my best.